Good morning, ladies and gentlemen. Welcome back. Before we start, I would like to show you a slide. This is the COVID-19 live war counts about coronavirus pandemic. I want to show you these slides because it's still in a very serious conditions. Total confirmed case 1.4 millions. That's the total confirmed case. And total deaths is about 82,000. And recover is shown here. Territory is here. Okay. United States has close to 400,000 cases. That's the largest. And some of the students come from China. Confirmed case and deaths are shown here. And also, some students from India. Confirmed case is about 5,000. And from Malaysia, okay, 4,000. Anything else? Okay, and also from other countries. We are here, actually still in a pretty good shape. However, in order to prevent the infection of coronavirus, our university encouraged us to continually using distance learning. That is, we will use online learning, maybe throughout this semester or next semester. Okay, so I wish we have a chance to meet at the classroom. However, because of the coronavirus, we probably cannot do that. So I would like to invite you to visit me at my office hour. You can visit me through the room or call me at my office during the office hour. Okay. Today we will talk about electric dipole and fields radiation. Actually, we have a pretty good shape. We make pretty good progress already. So it's not hurry. Today I will cover just 4 pages. Yes, just 4. So I will have sufficient time to refresh your memory, to review what we have learned so far. We will cover electric dipole fields, page 26, 27, 28, and 29. Just 4 pages, not too much. Okay, we will talk about electric dipoles. But our starting point is quite strange. We start from vector potentials. From our previously understand, if we want to know electric dipole field, we should start from scalar potentials, not vector potential. We should start from scalar potential V. But interestingly, we start from vector potential. So let me show you our strategy. Okay. Maybe we should talk about, give you overall pictures. We start from vector potential. And from vector potential, we found we can correlate it to electric dipole. Okay, that's the interesting part. And then we will calculate the fields based on this knowledge. So why we use electric dipole? Why we use vector potential? Why we use vector potential? Okay, why we use vector potential? Because vector potential and scalar potential are coupled. So why we use vector potential can be found here. Okay, this line. We can derive the E field from a knowledge of H field that's valid for outside the source. So Z is the characteristic impedance. K is shown here. And we know H equals curl of A times 1 over mu 0. This one times this one is H. Okay? And the triple product tells us gradient divergence A minus Laplacian A. And because of Lorentz gauge, divergence A gives us 1 over c squared partial phi partial t equals I omega because sinusoidal time dependent. I omega c squared phi. Okay, so divergence A is actually correlated to phi, scalar potential. And homogeneous wave equation also tell us homogeneous, that means without source. But we have oscillating source. We have current source. We have charge source. Because we are calculating outside the source. So outside the source, J and rho equals 0. Both equals 0. So it's homogeneous equations. Laplacian A can be changed to this form. 2 times time derivative minus omega squared over c squared times A. Okay, so this one gives us minus omega squared c squared over times A. So electric field now by substituting this one into here and this one into here, we got these properties. Okay, E field just equals to cancel c squared. I give us a minus. So minus gradient phi. And we have I omega. So it's plus I times omega. Cancel. So just 1 omega. C squared cancel with this one. So electric field equals minus gradient phi minus I omega times A. But we know this is phasor. In terms of we use exponential minus I omega t dependence, and then we can restore to its original form. Ext, that's real, minus gradient phi, xt, real, minus partial a xt partial t. Okay, so this is the original definition of E field. So outside the source, we can simplify E field to this form. Therefore, all we need to do is H. Once we have H, we have everything. H can be derived from vector potential. So all we need is vector potential. And then we can derive H. Based on the knowledge of H, we can calculate E. Okay? That's the logic, step by step. Okay, next step, how to calculate A. Let's move to page 1. Maybe here. Last time, I told you, if we want to calculate A, we need to have the knowledge of J, and we will use the idea of green function. You can start from outgoing wave boundary conditions. Starts from real part. So in that case, you got a green function with outgoing wave boundary condition. X, t, s prime, t prime is a delta function. However, many people prefer this form, time-independent form. We prefer using harmonic source. Everything is harmonic. Everything has the same harmonic time dependent exponential minus I omega t. So in that case, we can rewrite this one into exponential minus I omega t, just like separation of variable. Separate the space dependence and time dependence. So vector potential, phasor part becomes mu 0 4 pi d3 s prime exponential ik x minus s prime over x minus x prime j x prime. Okay, if k is very small, k is the wave number, that is the frequency is 0, then this one will be 1. That will be the simplest case, magnetostatic case. So we just verify with our previous understanding. If everything is static, then the equation will become very simple. The problem is how to expand this one. How to expand exponential ik absolute value s minus x prime over x minus x prime. How to do that? To do that, we need to have some knowledge. Let me show you what is the knowledge. We need to have the knowledge of spherical Bessel function and Hankel functions. That is, we will start from here. And this is Helmholtz wave equation, no source term, or time-independent wave equation, no source term, homogeneous. Helmholtz wave equation can be expressed in terms of spherical coordinates. And once again, because of the symmetry, we will use separation of variable. Once again, we use the separation of variable over and over again because it can simplify the calculation a lot. And by doing so, we will simplify into R dependence here, theta dependence, and phi dependence. Phi dependence because of azimuthal symmetry. Because of phi dependence, sorry, not azimuthal symmetry. Phi dependence is always simple. We like phi dependence. In our world, if you change the angle 360 degree or 720 degree, the same. So m must be integer. M must be integer. And how about L? L from here, it looks like it's still integer. Okay. And then we can assemble spherical harmonics. Spherical harmonics, just like our previous understanding. Okay. And R dependent is a little bit difficult. R dependence starts from here. Without this term, the solution is very easy. But because we have these terms, we can rewrite U as FL. We can rewrite U as FL. Oh, just rewrite. And FL equals 1 over R UL. So give us this one. Substituting this one, we got UL becomes Bessel function and Hankel function of fractional order. The subscript here is not integer, but it's a fractional order. So in terms of FL again, we got this one and this one. And we can redefine this one into JL, KR. Just define the S here. And Newman function shown here. Okay. The major difference is J is capital and smaller case. N is smaller case. This is spherical Bessel functions. Normally, Bessel function is associated with cylindrical coordinates. But here we found that it's related to spherical coordinates. And also, we can express spherical Bessel function as Hankel function of the first kind, Hankel function of the second kind. Okay. So in that case, psi x omega is a linear combination. It can be expressed as a complete function set. That's a complete function set. Okay? So you should keep this in mind. Any well-behaved function can be expanded as a complete function set. So next step, we will express green function in terms of this one. Okay, so let's go back to the green function. Okay, extension of the green function. Starting from here with source, the green function will be very easy. Okay, it's given by, it derived already. Green function x prime equals exponential ikx minus x prime over x minus x prime absolute value. In infinite space for outgoing wave boundary conditions. Actually, if you start from the very beginning, you will find in terms of delta function, they are correlated. We may solve equation 6.36 in the same way as in section 3.9. But I don't want to spend too much time. I just want to show you again. We can expand this green function into this form. Spherical Bessel function, spherical Hankel function of the first kind. Okay, so it's a little bit strange combination. Spherical Bessel function and spherical Hankel function of the first kind. Okay. Here is a summary of differential equation and their solutions. If we have Laplace equation, okay, in terms of Cartesian coordinates, the solution is simple for this one. In terms of cylindrical coordinate, we have Bessel function, Newman function, Hankel function. Okay. In terms of spherical coordinates, we have YLM, spherical harmonics, RL, R minus L plus 1. Okay. That's for Laplace equation. Helmholtz wave equation, we have extra term here. This term comes from omega, comes from time derivative. And in this one, quite similar. But this term is also complex. IKZZ. And cylindrical coordinates. Okay, we have Bessel function. We have this one, the same. And once again, wave can propagate, so it's exponential IKZZ. And in this one, wave cannot propagate, just confined in some space. And YLM theta phi. And here, see, that's the major difference. And differential equations with a point source that correspond to this one. Differential equation with a point source correspond to Helmholtz wave equation with outgoing wave boundary conditions. In this case, is zero boundary conditions at infinite. So the solution for the green function is very easy here. However, in this case, we have extra term. Okay? So we have series expansion of green function. We express this one in different notation, different expression. Okay, and this green function just shown here. This one. So we will use this green function extensively. Okay, another comparison. We have Helmholtz wave equations, time independent. We have wave equation, homogeneous wave equation, time dependent. Okay, and the solution for this one, we just display. And solution for this one, we need to perform integration. And not so differential equation with a point source is shown here. And with this point source, we use plus just to indicate the outgoing wave boundary condition. Of course, we have incoming wave boundary conditions. The solution for this one is an expansion for this one is here. And this one, we already talked about this one in Chapter 6, Retarded Field, Retarded Potential. Okay, so now let's keep this in mind. We are going to deal with differential equation with a point source. So we will start from this one. That is series expansion, this one. Okay, the next step is how to express this one. How to express this one. Okay, the green function. Here is the techniques. For expansion of our purpose is to expand this one. Exponential ikx minus x prime. Remember, that's equation 9.98. 9.98. And substituting equals this one. Substituting here equals this one. We can rewrite into this one. What's the difference? Oh, the source is always small. So it's a localized source. And observer is much, much far away. So R greater will be observer. R smaller will be source. So just keep this in mind. We separate into R smaller, R greater. Okay? In that case, after substituting this one into here, the source part will be still in the integrand. That's the source part. And that's the source part. And observer's part. Observer here. And observer here. And 4 pi cancel with 4 pi. So we have ik mu 0. Okay? Exactly the same. You can also start from equation 9.11. That's Jackson's strategy. Jackson just starts from equation 9.11. Okay? So, next step is to express Hankel function of the first kind into series expansion. And our strategy is let you know only. We just use these properties and we just extract from the handbook of mathematical functions. Okay, A is defined as this form. H is also Hankel function of the first kind can be expressed as this one. It depends on R, depends on R, depends on R. And it's a summation from n equals 0 to L. Here is a strange notation. That's the factorial. Factorial of a number n. Factorial of a number 2L minus n. That part is easy. Factorial of a number n, that is n times n minus 1 times n minus 2 times 2, 1. Okay? How about double factorial? Double factorial. Double factorial or semi-factorial is defined as here. Just look at this case. 2L minus 1 double factorial. 2L minus 1, 2L minus 3, 3, 1. Okay, that's for odd. How about for even, like this one? For even case, we start from here, end up at 2, not 0. So This is semi-factorial or double factorial. Okay, just we consider this as a knowledge. Just use this knowledge. We are user. We are not mathematicians, so we are physics major. So we will use these properties. Okay, so you can always start from here and substituting everything into here. Okay, that's the simplest techniques. So by substituting into this equation is an equation 9.11 is an exact expression for vector potential. Okay, and substituting everything into here, eventually we got this notation. Once again, we start from vector potentials. YLM is here is to be integrated. Oh, very similar. Very similar. Interesting. Maybe you will worry about spherical Bessel function, but under these conditions, wavelength is smaller than this one. It can be simplified into here. So actually we have three dimensions. Dimension D is the physical dimension of the source. And then wavelength and observer must be greater than D. So we have three conditions. D is always the smallest. Observer lambda is small. It's greater than R, let's call near field or static wrong. R greater than lambda is called far wrong or radiation wrong. And as for the intermediate or induction wrong, that's a little bit complicated. So normally we will omit this part. Intermediate or induction wrong. We will focus on near wrong and radiation wrong. And near wrong, just go back to static case. You can compare the result we obtained at last semester and here. Actually the same. So by using these approximations, we can simplify the notation a lot. Hankel function of the first kind can be rewritten into this form. Spherical Bessel function, spherical Hankel function. Okay, by substituting this one into here, we got this one. So you have two choices. Starting from equation 9.11 or starts from here. Starts from here seems to be much easier. Okay, let's move on. Okay, so we start from electric dipole. We start from here. Start from here, and we consider L equals 0. The lowest part, the lowest component. So y0, 0. L equals 0, so m must be equals 0. So y0, 0 is 1 over 4 pi, denoted as AP. Let me show you why is AP. AP, AX, L equals 0, mu 0, 4 pi. Where is the 4 pi? 4 pi is shown here. 1 over square root of 4 pi. And this one contribute another 1 over square root of 4 pi. So we have this one and this one give us 4 pi. Mu 0, the same. Exponential IKR here. R, L equals 0, so R here. And the integrand, we have Jx here. R prime 0, so it's 1. Nothing here. So we have this integration. This integration gives us something interesting. See the right hand side. Let's consider Jx. Jx x component. And you can consider y component and z component. Jx, jy, jz separately. Okay? And you can use integration by parts. X, jx, so x, jx minus x partial jx partial x dx. Okay, that's integration by parts. But we know one thing. Jx close to the edge. That is the d is the size of the localized source. We just choose the range slightly larger. The source is localized. So you just change the integrand. The range is slightly larger. Then this part will be 0. So all we need is consider this one. Cover all the space. Okay? So this one contribute nothing. And once again, we can add another 2. Why this 2? Because after integration, this one also contribute nothing. Because of this knowledge, source is localized. So adding these 2 terms doesn't change anything, but doesn't contribute any extra terms. But we can rewrite this one into divergence J. Okay, so J integration, J volume integration give us minus here, x here, divergence J. Jx give us this term. Jy will give us y divergence J, and Jg give us minus z divergence J d3x. So divergence J is always the same. So J give us x. So we can change the integration from volume integration of J to minus x divergence J d3x. According to conservation of charge, divergence J can be rewrite into minus partial rho partial t. And because of independent harmonic time dependence, this one equals minus I omega rho x. So this terms volume integration of x times rho give us dipole, electric dipole, P. So eventually volume integration of J give us minus I omega P. Okay, so that is this integration give us minus I omega P minus I omega P, and this part exponential IKR the same, over R the same, mu 0 the same, 4 pi, yeah. Okay, so interestingly, from vector potential, as we can calculate electric field strictly from vector potential. And the zeroth order L equals 0, the vector potential is actually correlated to electric dipole. So, very interesting. Yeah. This equation, 9.16, gives the electric dipole contribution to the solutions. So everything is connected. Okay. Although we need to use some knowledge of this one. If I don't write it down, it will be very difficult to understand. So I think it's very important, useful. Okay, what's next? We can rewrite equation 9.16 here. And then we can calculate H field using this knowledge, 1 over mu 0 curl of A. The P denotes electric dipole. Okay, and then for outside the source, E field is related to P. So this one L equals 0. We got this one, AP. And P is related to electric dipole. And with vector potential, we can calculate H field. We can calculate E field. So by substituting this one into here and this one into here, eventually this one into here and this one into here, eventually we have these solutions. I don't expect you to derive these equations by yourself. That's for advanced students. For students who are very interested in the derivation. Okay. Otherwise, you can consider this one as someone already derived this equation for us. All we need is use. We can use these properties. Okay, HP equals ck squared over 4 pi n cross p exponential ikr over r 1 minus ikr. Okay, so we got everything. Next step, what's next? Next step is we can consider near wrong, far wrong. Okay? If we consider far wrong, kr is greater than 1. Okay? What will happen? Far wrong, that is, source is localized. Wavelength is large than source. And observer is much larger. So KD is small, but KR is very large. KR is very large, so you can omit these terms. And R very large. Once again, omit these two terms. Just 1 over R. 1 over R. Higher order term can be omitted. So in the far wrong, we have this one survive. ck squared over 4 pi n cross p exponential ikr over r. And E field d0 hp cross n. Okay, hp is shown here. So eventually we have a very simple expression for far field. we see that EP and HP are in phase. In phase. EP and HP are in phase and perpendicular to each other. Mutually perpendicular. This is a general property of EM field in unbound uniform space. Given any two of these quantities, we can find the third. What is N? N is the direction from the source to observer. So just like pointing vector, we have E cross H give us the pointing vector. Okay. So their relation is simple, just like spherical wave, just like plane wave. Okay, let me write this equation again. In a near room, Kr is smaller than 1, and equation 9.18 reduces to Kr is smaller than 1, smaller than 1. So in this case, you have Ik cancel with K. C HP, we have CK squared over 4 pi and 1 over R the same. Exponential IKR can be rewrite into 1 plus IKR plus high order terms. 1 minus IKR here. Approximately equals here. We can omit high order terms. Omit high order term. This part the same, this part the same. And this one is very, very small. 1 minus 1. And then we can just consider this term. So eventually, we just consider these terms. Okay? That's interesting. CK squared over 4 pi. So K cancel with K. Eventually, we just consider CK over 4 pi N cross P I R squared. I move to the front. ICK equals I omega. Okay, so we derive this one. And EP approximately equals this one. That's distance. And we consider the most important terms. Most important terms here. And this one is very small, just 1. So 1 over 4 pi epsilon naught times 3 n dot p minus p 1 over r cubed. Okay, so in a near room, the relation is different. Near room, we have I here, and we have no I here. So in near room, they differ by 90 degrees. They are out of phase. Therefore, in a near room, the average power E cross H, take time average, take real power, give us nothing. So average power will be 0. And second, EP has the same spatial pattern as that of the static electric field, but with exponential minus I omega t dependence. Mu 0 times h squared, where? Okay? So in a near field, electric field energy is greater than magnetic field energy. That's interesting. At far field, electric energy and magnetic energy are equals. However, in the near field, okay, in this case, because electric dipole we still have one more slide. That is dp over the omega takes the time average. So it's time average power. P means power in a far wrong per solid angle. Unit solid angle per unit solid angle. So it's 1 over 2 average power. So take the real part. R squared N dot EP cross HP complex conjugate. And 1 over 2 just express time average. Remember, E and H are in phase. So time cosine square, cosine. So it's cosine square. After time average, it gives us 1 over 2. Sine square. After time average, gives us 1 over 2. So anyway, this part, time average, gives us 1 over 2. And we need to take the real part. And to calculate the unit solid angle, we need to times r squared. Okay? Times r squared. And equation 9.19, substitute to here. We got this one. Not that easy. So let me write it down. R squared N minus EP cross HP star equals R squared N Z0 HP cross N cross HP star. Okay? Z0 can move to the front. R squared the same. N the same. And HP come back to this slide here. HP is shown here. CK squared over 4 pi N cross P exponential IKR over R. Okay? The coefficient is moved to the front. N cross P, that's exponential IKR, that's exponential minus IKR. CK squared, okay, 4 pi, R, we have R squared, cancel with R squared. So Z0 the same. C squared K to the fourth over 4 pi squared, the same. Okay? So, what's next? N cross P cross N cross N cross P. Okay? How to calculate this one? How to express this one? You can use the triple product. Just consider this one as A, this one as B, this one as C, and then substitute to here. Step by step. Eventually, you can rewrite into this form. Okay. Personally, I prefer to keep it here because it's much easier to understand. All you need is just put everything here, and you have no feeling here. Actually, the same. So these vectors gives the direction of EP. That is the polarization of the radiations. Okay, you have no feeling about this word. So power average, we need to R squared. Total power radiated. I just write it down without explain. In general, P can be in the x direction, y direction, or z directions with alpha equals beta equals gamma. Then P has the fixed directions. P0 exponential. If they are in phase, okay, then P has a fixed directions, exponential minus I alpha. And P can be read in x direction, y direction, z directions. Okay. We prefer P is in the z directions. That can simplify the calculation a lot. So the P over the omega in this case. And we can simplify into this form. Okay. Theta is the angle between P and observer. So although in this case we have three directions, we prefer to align the dipole to the z directions. So by doing so we can simplify the notation a lot. P just in the z directions. So eventually we can use this one or use this one, and we will got this one. C squared, the same. 4k to the fourth, 32. 16 times 2, 32. Pi squared, pi squared, pi squared. Okay? P squared, P squared, sine theta squared. So, theta is the angle from the z-axis. So, angle from the z-axis. And it will generate E here, H here. And N is the direction of propagation, just like pointing vector at far field. So E cross H gives us pointing vector X. N is the direction of the pointing vector. So, so it's much easier to understand. So radiation pattern looks like this one. Looks like donut shape. Okay? So if we have an antenna look like this one, and the radiation pattern from z-axis, we have nothing. It's localized. Oscillation is here. The strongest will be theta equals pi over 2. So in this angle, pi over 2, that's the radiation pattern, three-dimensional view. That's the radiation cross-sectional view. Dipole radiation pattern. Dipole radiation pattern is relatively easy to understand. So we can substitute everything. We got these equations. Vector here is the vector identity. Just provide you for some knowledges. You can change the order, change n here, or you can triple product, vector triple product. So now we have the electric dipole. Next step is magnetic dipole. Okay, I will quickly go through the following pages. Okay, so next step is calculate magnetic dipole and higher order terms. Normally, electric dipole and magnetic dipole are good enough. Higher order terms are not very critical. Not very critical. So you can start from here and consider L equals 1. So A1 will be equals minus 1. L equals 1. We will have these terms. And YLM, put everything inside. And you can rewrite this one into electric quadrupole radiation, magnetic dipole radiation. We separate a vector potential into AQ plus AM, and AM will give us these properties, quite similar to AP, quite similar. And based on this one, we can calculate HM and EM. Okay. Once again, I don't expect you to derive this equation by yourself, but you need to have some idea about how this works, how to calculate this one. You have a picture about uh, about the how to obtain E field and B field at different ROM. And as for the mathematical details, you can consider it as a knowledge. Okay? And in a far ROM, that's the result. Quite similar, right? In a near ROM, okay, here. Okay, electric quadrupole is not very critical, so skip electric quadrupole. And here is a comparison. Comparison between static and time-dependent cases. This is a very useful table. We will talk about this part next time. Okay? Then we will consider center fade linear antenna, or center fade, that is feed from the center. Center fade linear antenna. Actually, from this center fade linear antenna, we can have some idea about phase array, how to synthesize the radiation, how to synthesize the radiation pattern using such a simple structures. Okay? So I do wish to have a chance to teach you, but sorry, because of coronavirus, we cannot do that. So you can study at home or any place you want. That's another advantages. Okay, if no other questions, I will stop here. See you next time.